is inventing these, and this is the order parameters E0, E1, E2, E3. And in the context of what we're doing, these are not independent of each other. It turns out that they're related. The constraint between them is that E0 squared plus E1 squared plus E2 squared plus E3 squared equals 1. All right, so this is a constraint between them. They are not three free independent variables. They are related by this. And we'll explain how this actually shows up in the rotation matrix in a second, and where this comes from. When you're doing integration, it's not uncommon for you to what's called renormalize the Euler parameters, and it's pretty easy to do. What you do is you start off with E0, E1, E2, E3 equal to whatever, it doesn't really matter, and then you reset E0 along the way. And what you'll do is you'll say E0 is equal to E0 old divided by E0 old squared plus E1 old squared plus E2 old squared plus E old squared. Okay. So we do this a lot where we'll take this sum, which might not be 1, okay? This may be equal to, for example, 1.2. So this bottom thing should be 1. It's not. So we say, well, how do we go back and give me this constraint to be renormalized? What you do is you reset E0 to be whatever E0 was and divide by this thing squared. So that's renormalizing, and so it's such an easy thing to do to say, if this isn't staying 1, don't worry, it's really easy to fix it. And to make it go back to renormalize to 1. All right, so that's sort of the history of them. This is how they relate, and then you'll hear people talk about quaternions a lot, but in terms of our usefulness of them, this is a huge field. It, like I said, dominated the mathematical landscape, and then people finally realized, you know what, vectors own the game, really own the game. What do you really need to know? You need to know a tiny subset of quaternions called Euler parameters. And so when people talk about quaternions, they're usually talking about Euler parameters, but they're slightly different. It's like saying, no, the parameters are these things, the quaternions the whole thing, and then you can do all kinds of quaternion algebra, which you don't need to know. All right, so that's what we're going to do. So as a second methodology for doing 3D, we're going to do quaternions, otherwise known as Euler parameters. The advantage really is literally avoid singularity. That's why you care so much. The disadvantage is it's even more mathematical. Okay, it is in la-la land. So it's la-la math. All right, there's nothing physical about it. Nothing. So when people say, what does it mean? It means nothing. It's a change of variables. It is a pure math game. All right, but in order to get to quaternions, there's one more thing, one of the, it's called a method for doing rotation. So these are all, by the way, these are all about so there's one more set. This is all about rotations. So the last set is what we call axis angle. All right, and its advantage is it's super physical, completely easy to understand, and it's the gateway to Euler parameters, quaternions. So that's what's great about this. The complete disadvantage is here the singularities are, I'll say at 90 degrees. These have singularities, and even the worst place is 0 degrees. Okay, so like you can't even start with these things. So they're pretty much useless when you relate them to angular velocity, but they're the gateway to these things, and they're really easy to get a hold of. So first, let's talk about the axis angle. Then we'll talk about the quaternion, and then we'll get to stop. All right. So I want to first talk about axis angle. Your books, you have a this is chapter 9 in your books.
There's leftover stuff in the lab barbecue that you can all help yourselves to. So.
Thank you, Alex, for bringing that in.
Yeah,
I'll help you afterwards.
There's plenty on it.
So we're going to start chapter actually 8, so 0.5, chapter 8.5. And so this is where it starts. So one way to do general orientation is to use 3 angles. That was the roll pitch yaw. So you can say, I'd like to be able to orient this any way I want. And you can think of this also as a piece is moving down an assembly line. The piece is moving down the assembly line, it's on the assembly line, it's going that way, and all of a sudden you say, well, in order for me to make my next drill or next move on this thing or fill it up with whatever it needs to be filled with, you actually have to change the orientation of it. So it's coming down the assembly line, you decide you have to actually get it to look like this. And you can do it by doing 3 things. You can actually have 3 pieces of equipment, one that does a rotation one way, one that does a rotation another way, one does a rotation another way. So you can build 3 pieces of equipment, or you could say to yourself, is there a way for me to be really clever and find the right axis to do the rotation about? And if I do the rotation about the right axis, I could just do 1 piece of equipment move. And that's what we're actually going to do, and that's called a single axis angle rotation. So this is called we call this a simple beta lambda rotation. And of course, who came up with the math to this? It is Euler. Of course, he did everything. And so what he said is, here's what you do. If you want to do a reorientation, here's the math to it. I mean, the math is in the book. It's very mathematical. But I'll just give you what happens how to start this pictorially. So here's a set of 3 unit vectors, and then here's an object. B, and inside of B, initially aligned with A, is Bx is this way, By is up, and Bz is up. So we start with B initially aligned with A, and if you say, I could rotate first around Bx, you'd say, okay, great. I know you've been doing that all quarter. You're like, okay, if you rotate around Bx, I know exactly how to handle this. If you rotate just around By, I know how to handle this, or I rotate around Bz, I know how to handle this. However, sometimes you want to rotate around some combination of bx, by, bz. And we talk about that combination as being unit vector lambda. So lambda is equal to, and we call it lambda 1, something in the bx direction, plus something in the by direction, plus something else in the bz direction. So the stuff you've been doing up to now, the easy stuff, would be lambda 1 equals 0, lambda 2 equals 0, and lambda 3 equals 1. That would be just a simple rotation around BZ. You know what to do with that. You know how to find your rotation matrix. So with just a little bit more math, it's not that hard, you can say, I'd like to rotate not around BX and BY, BZ, but some combination thereof. What does my rotation matrix look like? So what happens to this R? And the answer is, it turns out it's not terribly, the math isn't super complicated, but it's a little bunch of sines and cosines, drawing pictures, doing some Sakatoa, right? And it's all in the book. But what you end up with is, I'm not sure, the shadow's not so bad. R, A, B. And we end up with, here's AX, AY, AZ. And the first element is cosine theta. That's the angle that you did the rotation, plus lambda 1 squared times 1 minus cosine theta. So this is how AX relates to BX when you do the rotation. So the easiest thing to see in doing this is to take a book and say you could rotate around BX or BY or BZ, or you could just rotate along the diagonal, okay? And I think it's really simple to understand that. You say, well, if I rotate around the diagonal, it's not BX or BY, BZ, it's some combination. Now, granted, it's only, this might be non-zero, this might be non-zero, and that would be 0. So square root of 2 over 2, square root of 2 over 2, 0. And what that does is it would take, this time I'm going to bug you, not drop it. All right, your job is to hold that corner there. All right, and our job is to then rotate this, okay, about the diagonal. All right, I'm going to rotate it on the deck. So we're going to rotate this. We rotate by an angle theta. All right, so that would be like 45 degrees. If we rotate by 90, this would be a 90 degree. All right, so that's what's meant by theta. So you pick any vector to rotate about, and then you rotate it by a certain angle. And then you say, what happens to the orientation? Well, it turns out you can put it into any orientation doing this, and theta is the angle that you rotate by. And for this case that we just did, this lambda 1 is square root of 2 over 2. This one's square root of 2 over 2. And that one's 0. So that's BX. There's BY. There's BZ. I'll just give you a few of the elements because the rest are in the book. And the book does, I think, a pretty good job of getting it. So this one is lambda 3 sine of theta plus lambda 1 lambda 2 times 1 minus cosine theta. And the next one is negative lambda 2 sine theta plus lambda 3 lambda 1 minus cosine theta. And so on. Okay, so then you get two more elements. And the last one I'll just write down as cosine theta plus lambda 3 squared times 1 minus cos theta. So you get these elements, and you get a very physical thing. You just literally you pick a vector anywhere on the block and just rotate about it. All right, so very physical. Now someone says, I'd like you to compute this rotation matrix. I give you theta, and I'm worried about your computational cost. I say, I want you to compute this rotation matrix really efficiently, all right? And you start calculating, like, how many computations does it take? Well, you start off with a lambda 1 squared. Now, square is actually a pretty straightforward, it's just a multiply. Okay, so this is a multiply cheap. A plus is relatively cheap. On new machines, the plus and multiply all take about the same amount of time and they're very small. But then you run into the cosine. All right, does anybody have any idea what the factor of, like if this is a 1 and this is a 1 in terms of cost. So plus is about 1 and multiply is about 1. Does Does anybody know what a cosine is in terms of cost relative to 1? Take a whack. Ken, just take your best guess. Is it 2? Is it a factor 2? Is it a factor 4? All right, so give me your best number. Just go around and throw me a number. 10.
50.
50.
60.
60.
2.
2.
10.
10. Okay, we got a good sampling. I'll come back to you guys later. So 50, it turns out, is the number. So it's a factor of 50. Play the lottery today. All right, so it's very expensive to do this cosine. Cosines are really tedious. Sines and cosines have heavy overheads. Why? Well, if you remember, and you do, I'm sure, this is 1 minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial plus minus minus theta to the 7th over 7 factorial plus, dot, dot, dot. Okay, so this is calculated through a Taylor series expansion, really expensive calculation, and sines and cosines aren't cheap. And you actually have a sine, I believe you also have a sine in there as well.
Yeah.
Sine, yes, there's a sine in there as well. So you have a sine in here, you have a cosine in here. It turns out this is expensive. So you start looking at it and go, is there a way for me to not do this calculation? Now again, there are 4 variables here. The variables, the unknowns, that you worry about are things you care about. I'll just say the parameters are lambda 1, lambda 2, lambda 3, and theta. Is there a relationship between these? Yes, there's 4 parameters. What is the relationship? And now we'll take the other side of the table. Andrew, what's the relationship?
So lambda 1 plus squared plus lambda 2 squared plus lambda 3 squared is 1.
Good, and where did that come from?
Assuming lambda is a unit vector.
Exactly. So when we get to the Euler parameters, it will turn out that's exactly what's going to happen with the Euler parameters. They follow directly from this idea that this is a unit vector you're doing. So the constraint is, those are the parameters, and there's a constraint that lambda 1 squared plus lambda 2 squared plus lambda 3 squared equals 1. And that's just because of it being a unit vector. Okay? So you have a constraint, so you have 4 of these. And given those 4, you can calculate these things. So given those 4 numbers, lambda 1, lambda 2, lambda 3, you can do the calculation. Here is its number. Now someone says, that's lovely. I would like to form a different version of this by doing some super clever math and doing a change of variables. So we'll do that. And the change of variables we'll use, all of it involves basically just trig identities. It will turn out that we're going to use half-angle formulas in trig to do a change of variables. And guess who did that math? That was, of course, Euler. He said, this is hard. Because, you know, at this point, don't forget, his children were doing his calcs. I mean, he had a bunch of kids, and he's like, go, do your calculations. And the kids were like hungry, and they come home, and 2 hours later, they get the cosine, you know? So he said, okay, this isn't such a good way. Let me see if I can dream up a faster way for you to get dinner. So he did, and so the way he did it was he said, I'm going to introduce and invent this thing where I'm going to say that E0 can be defined as just cosine of theta over 2. Right? So this is the first thing. And all of this is just to take this stuff and make it into something that's actually easier to compute. So the first thing he said, I'm very clever. I know all the half-angle formulas again. All this is in the book, but it's not obvious. But once you see it, you go, wow, that wasn't so bad. So this is E1. He just said take lambda 1 and then multiply by sine of theta over 2. And same thing for E2. I just have lambda 2 times sine of theta over 2 and E3. Okay, so this is the invention that he did, and what it does to here is actually just incredibly brilliant. It takes the rotation matrix, and I'll just again write out just a few terms. And the terms that I'll write out are here, 2E1 squared plus 2E0 squared plus, minus 1. That's the first term. The next one is 2 times quantity E1, E2 plus E3, E0. And the last one is 2 E1, E3 minus E2, E0. All right, so now we start counting, let's say, and there's a few more here, but they look very similar. All right, and now you start counting how much does this cost? So given the parameters, so here are your parameters now. So someone says, great, here are your parameters, and they're E0, E1, E2, E3. What's your cost for calculating the rotation? Let's make sure you can see. And you realize, okay, that's basically a multiply. That's a multiply. Add and subtract. Multiplies by 2. So you're looking at like roughly 6. There's 6 operations here. You come over here, forget about the cosines, you still have the 2, you have to subtract, so it's a multiply, a subtract, another multiply, and an add. So you're already at roughly the same. You're not like skipping the cosine, you're like, this is almost exactly the same computational cost as this if cosine was already pre-computed. So this turns out to be incredibly more efficient. There are no trig functions here at all. So there's a major gap in